Good morning, students. Welcome back to session 15 of linear transformation class. In the previous classes, you have studied what's one point Hermitian transformation, unitary transformation, normal transformations, and theorems based on these concepts. Okay, and also we have solved few problems related to these concepts also. So let us take up the next concept in this class, which is the orthogonal transformation and the symmetric transformation. Okay, yes, let us take up the definition first. Say if U is an linear operator on a finite dimensional inner product space over the real field. It is to be noted here, it is over the real field. Okay, a operator U on a finite dimensional inner product space over the real field, and if U star is same as U inverse, if U star adjoint of U is same as U inverse, or equivalently U into U star is equal to I, that's equal to U star into U, then U is said to be orthogonal. Understand this? So here in the previous class we have discussed about the operators which are defined over the finite dimensional inner product space over the complex field. Here it is defining over the real field, and there this condition is called the unitary operator condition. Here it is called the orthogonal operator condition. So unitary condition is nothing but the orthogonal condition here, right? Understand this? So U star is equal to U inverse, or U into U star is equal to I, that's equal to U star into U. The matrix A with real entries represents an orthogonal operator U if and only if A transpose is same as A inverse. A matrix A with a real entries represents an orthogonal operator U, or the matrix itself is called the orthogonal matrix if A transpose is equal to A inverse. Okay, A transpose is equal to A inverse, that is defined here. So a real matrix A for which A transpose is equal to A inverse, or A into A transpose is I, which is same as A transpose into A, then it's called an orthogonal matrix. Okay, an operator, a linear operator T on a finite dimensional inner product space over the real field is called symmetric or self-adjoint if T is equal to T transpose. If T is equal to T transpose, there T is equal to T star means it is Hermitian. Here it is called the symmetric operator. Therefore, the Hermitian operators on a finite dimensional inner product spaces are called the symmetric operators. Note that a real symmetric matrix can be brought to diagonal form by an orthogonal matrix. A real symmetric matrix can be brought to diagonal form by an orthogonal matrix. Okay, so now let's consider this concept. Say let A be a real symmetric matrix. Means is matrix with entries which are reals, as well as it is symmetric, means A is equal to A transpose. Then if we consider A as acting on a real inner product space V, real symmetric matrix means then we consider A as acting on the real inner product space V. Now if we consider this matrix A as a complex matrix, then it becomes Hermitian. So that all its characteristic roots are all real. That we have proved. If T is Hermitian, then all its characteristic roots are real. Now let lambda 1, lambda 2, etc. lambda k be the distinct eigenvalues of T or A here. Then we decompose V as direct sum of V1, V2, etc. Vk, where each Vi contains set of all Vi belongs to V, such that A minus lambda I power of Li of Vi is 0. Here A is treated as a matrix as well as the transformation. Okay, so Vi is equal to set of all Vi belongs to V, means set of all those vectors belongs to V, such that A minus lambda I power of Li of V is equal to 0. Okay. Now since A is Hermitian, it is normal. It is normal. So that A minus A lambda is also normal, that we have proved. If T is normal, T minus lambda is also normal, that we have proved. So A minus lambda is here normal. But we know that if n is normal, then nk of v is 0 means n of v is also 0. Accordingly, if A minus lambda power of li is normal, and then we can declare that A minus lambda of vi is also normal. According to that result, we can declare that A minus lambda power of li of vi is 0 implies A minus lambda of vi is 0. This implies A of vi is equal to lambda into vi. Therefore, lambda becomes the eigenvalues and vi become the corresponding eigenvectors. And also we have proved the eigenvectors are as orthogonal. Orthogonal we have proved, and since these lambdas are all distinct eigenvalues of A, and A of vi is equal to lambda into vi, we have inner product of vi comma vj is 0 for I is not equal to j. This also we have proved in the last class. Thus we can find an orthogonal basis of V consisting of eigenvectors of A. Thus we can find orthonormal basis of V consisting of eigenvectors of A. Then now here the change of basis from orthonormal basis 1 0 0 0 1 0 etc 0 0 1 to this new basis v1 v2 etc vn is accomplished by real unitary matrix, by a real unitary matrix. That is, it is by an real unitary matrix means it is by an orthogonal matrix. Real unitary matrix is nothing but here orthogonal matrix. For I will show this. Let EI is equal to the linear sum of AI1, F1, AI2, F2, etc. AIK, FK. You call by this number 1. So I have written only the ith element. Okay, where Fj is what? So Fj contains all zeros except 1 in the jth place. Now EI's are orthonormal implies what will happen? Delta ij is nothing but EI inner product of EI comma EJ, that is 1 if I is equal to j, 0 if I is not equal to j. That is called the Kronecker delta ij. So if you take the inner product of EI with EJ, what do you get? AI1 into S, AI1 into AJ1 conjugate plus AI2 into AJ2 conjugate etc. AIK into AJK conjugate. You call by this number 2. Now let B be the matrix with entries Aij, be the coefficient matrix of this 1. Let B be the coefficient matrix of 1. Then B transpose is the transition from where to where? Then B transpose is the transition from Fi to Ei. Then B transpose is the transition matrix from Fi to Ei. Therefore, B into B star is Cij, where Cij is what? Ai1 into Aj1i, Aj1 conjugate plus AI2 into AJ2 conjugate etc. AIK into AJK conjugate. Then by 2 what will happen? Cij is nothing but delta ij. Cij is nothing but delta ij, and therefore Cij is nothing but delta ij means B into B star becomes I, because I means in the unit matrix A11 is 0, A11 is 1, A22 is 1 except all other terms are zeros. Okay, means ANN 0, ANN is 1, A12, A23, A45 everything is 0 means what? See, delta ij means when I is equal to j it is 1, for other values it is 0. Okay, accordingly B and hence B transpose are unitary, and hence B and B transpose are unitary. If B and B transpose are unitary, then definitely you can bring A to diagonal form by an orthogonal matrix. Okay, understand this? So if B and B transpose are unitary, but every unitary matrix that can be bring into diagonal form, therefore A can be bring into diagonal form by an orthogonal matrix. Okay. Now say alternately the above results can be sum up as, see here, if A is a real symmetric matrix, then there exists an orthogonal matrix P, there exists an orthogonal matrix P such that B is equal to P inverse AP or P transpose AP is diagonal. If A is a real symmetric matrix, then there exists an orthogonal matrix P such that B is equal to P inverse AP or P transpose AP is diagonal. So now I will take another lemma which will be helpful in the proving next results. Say this lemma says if W is a subspace of V invariant under the unitary transformation T, then orthogonal complement of W, that is W perp or W perpendicular, the orthogonal complement of W is also invariant under T. This type of results we already taken up. Anyway, I am proving it again. So let W belongs to W and X belongs to its complement. Okay. Then inner product of T of W comma T of X. T of W comma T of X can be written as, you transform this to here, it becomes T star into T of W comma X. Since T is assumed to be a unitary transformation, T into T star or T star into T is I. Therefore, T star into T is I into W comma X. I of W is W itself, X. W comma X is because X belongs to W per, and W belongs to W means inner product of W comma X is 0. Thus, T of W comma T of X is 0. Now they were given W is invariant under T. W is invariant under T means what? If W belongs to W, then T of W is also belongs to W. Now you see this. Now T of W, this is an element of W. Inner product with some element is equal to 0 means this element belongs to where? This element belongs to the orthogonal complement of W, which is nothing but W perp. T of X belongs to W perp. Thus, X belongs to W perp implies T of X also belongs to W perp. Therefore, we can conclude that W perp is also invariant under T. If W is invariant under T, then orthogonal complement of W, that is W perpendicular, is also invariant under T. Okay. Yes. Let us take up this example now. So suppose A is the matrix with entries 2, minus 2, minus 2, 5. We need to find an orthogonal matrix P such that P transpose AP is diagonal. We need to find an orthogonal matrix P such that P transpose AP is diagonal. So for this, first we find the characteristic polynomial delta T of A is delta T is equal to Ti minus A is equal to 0 or implies T minus 2, 2, T minus 5 under determinant this is equal to T minus 6 into T minus 1. Now delta T characteristic polynomial, the eigenvalues are given by delta T is equal to 0 and it gives 6 and 1 are the eigenvalues. Now substitute T is equal to 6 into the matrix Ti minus A. We get Ti minus A as 4, 2, 2, 1. If you return this in system of equations, you get 4x plus 2y is equal to 0, 2x plus y is equal to 0. So the non-zero solution of this system of equation is, one of the solution is V1, I'll that call it as V1. V1 is 1 minus 2. Now substituting T is equal to 1 into the matrix Ti minus A, we get the corresponding homogeneous system as in the above. This gives minus x plus 2y is equal to 0, 2x minus 4y is equal to 0. Again, the non-zero solution of this system is V2 is equal to 2, 1. First one is V1 is 1, 2, 1, minus 2, V2 is 2, 1. Now clearly we can see that V1 and V2 are orthogonal because if you consider the inner product, their inner product will found to be 0. Now they are orthogonal. Now I will make them to be orthonormal. To make them to be orthonormal means we need to make them unit vectors. So I consider U1 is equal to V1 by norm of V1, U2 as V2 by norm of V2. Then what will happen? U1 and U2 are orthonormal. Then U1 and U2 are orthonormal vectors. Let P be the matrix whose columns are U1 and U2. You consider P to be the matrix whose columns are these orthonormal vectors P1, U1 and U2. So I written 1 by root 5 minus 2 by root 5 1 and 2 by root 5 1 by root 5. So you consider P inverse for this. So you find out P inverse and you find that P inverse AP or P transpose AP is nothing but it gives 6001, which is diagonal, Okay. Here one thing to be noted here, an orthogonal operator T need not be symmetric. Orthogonal operator T need not be symmetric, and so it may not be represented by a diagonal matrix. An orthogonal operator T need not be symmetric, and so it may not be represented by a diagonal matrix related to an orthonormal basis. However, such an operator T do not have simple canonical representation that I will describe in the next theorem. Okay, so that we will discuss in the next theorem, that is stated as, look here. So if T is an orthogonal operator, on a real inner product space V, then there is an orthonormal basis with respect to which T has the following form. This is a very big canonical forms. Look here. So it contains entries 1 1 1 on the diagonal, next minus 1 minus 1 minus 1 on the diagonal, and then we have a block matrices cos theta 1 minus sin theta 1, sin theta 1, cos theta 1, etc. up to last is cos theta r minus sin theta r, sin theta r, cos theta r, totally this under the one matrix. This is a very big canonical form. Okay. Say for this, let us take up one by one. Let S be the sum of T plus T inverse or T plus T star. Okay, I understand this because it is orthogonal matrix. So this becomes T plus T star. Then S star becomes T plus T star whole star. That gives T plus T star itself, means is equal to S. Therefore, S is symmetric. But if S is symmetric, what will happen? Then there exists an orthogonal basis of V consisting of eigenvectors of S. Okay, consisting of eigenvectors of S. Therefore, I will take lambda 1, lambda 2, etc. lambda m be the distinct eigenvalues of S. Okay, then we can decompose V as a direct sum of. So this is a repeated step. So V is equal to V1 plus V2, etc. Vm, direct sum, where each Vi consisting of eigenvectors of S belonging to the eigenvalue lambda I. Clearly, each of these subspaces are invariant under T, that we can show it now. Okay. Now since, look here, so now since each of these Vi's are invariant under T, okay, so each Vi is orthogonal also. We calculate the matrix of T on each of these Vi's, Now on a given Vi, T plus T inverse of V is what? S of V. S of V is what? Lambda times of V. Because Vi consisting of eigenvectors of S belonging to lambda I. This implies T plus T inverse of V is equal to lambda I of V. You multiply by T, we get. So if you multiply by T and transform this to left hand side, we get, say, look here, we get T square plus lambda I into T plus I of V is equal to 0. T square minus lambda I into T plus I into V is equal to 0. So now if you solve this, you get like, consider the two cases. Lambda is equal to plus or minus 2 and lambda is not equal to plus or minus 2 separately. If lambda is equal to plus or minus 2, then what will happen? Lambda is equal to plus or minus 2 means T plus or minus I whole square of V is equal to 0, which gives T plus or minus I of V is equal to 0. This implies T of V is equal to, okay, T of v is equal to, or else now here we taken lambda is equal to plus or minus 2, then this becomes T plus or minus, if lambda is equal to plus 2 you take plus 2, it becomes minus 2, it becomes T square plus 2T plus 1. Okay, so this becomes, so T plus or minus I whole square of v, or T plus or minus I of v is 0, or T of v is equal to plus or minus I times v. Thus T restricted to this vi is either identity matrix or minus I. If lambda is not equal to plus or minus 2, then T has no eigenvectors in vi. Since the only eigenvalues of T are, if lambda is not equal to plus or minus 2, then the only eigenvalues of T are 1 and minus 1. Because T is orthogonal implies all the eigenvalues of T are of absolute value 1 only. T is orthogonal implies all the eigenvalues of T are of absolute value 1. Hence, for non-zero V, the vectors V and T of V are linearly independent. Linearly independent. Now, look here. Let W be the subspace of V spanned by this vector V and T of V. Then clearly you can see that this W is invariant under T, because T of W is equal, T of V is equal to T square of V. T square of means T of means lambda into T of V minus V, that's equal to, that belongs to W itself. Also each of these VI's are direct sum of W plus W perp. Okay, so and W perp is also invariant under T. We have proved this. Okay, thus we can decompose Vi into direct sum of two-dimensional subspaces Wj, where Wj are orthogonal to each other and each Wi is invariant under T, and each Wj is invariant under T. Thus we can decompose Vi into direct sum of two-dimensional subspaces Wj, where Wj are orthogonal to each other and each Wj is invariant under T. Okay. Now we find the matrix of T on each of these Wj's. Now we find the matrix of T on each of these Wj's. Now since T square minus lambda I into T plus I is equal to 0, the characteristic polynomial delta of T acting on Wj is what? Delta of T is equal to T square minus lambda I into T plus 1. Thus the determinant of T is 1. The constant term in delta of T. But any 2 cross 2 orthogonal matrix, look here, but any 2 cross 2 orthogonal matrix A having the determinant value 1 is of the form is cos theta minus sin theta cos theta for some real number theta. By the above result, what will happen? The matrix represented according to this result, by the matrix A representing T acting on each of the subspaces Wj relative to any orthogonal basis of Wj must be of the form again cos theta minus sin theta cos theta. Now you combine all the bases of Wj gives the orthonormal basis of Vi. If you combine the orthonormal basis of Wj's, then we get the orthonormal basis of Vi, and the union of basis of Vi gives the basis of V. Aren't so now? So each of these Vi being split as sum of two subspaces sum of subspaces of Wij. Wij of matrix of this form, and combining taking all the basis of Vi's, we get the basis of V. We get the basis of V in which the matrix representation T is of the desired form. Which is as 1 1 1 1, one block, minus 1 minus 1 minus 1, another block. Next is cos theta 1 sin theta 1 cos theta 1 etc. up to cos theta r minus sin theta r into cos theta r. Okay, so that is the required form. Now we will show the concept that we have assumed in the above proof of above theorem. So there what we have assumed, a very 2 cross 2 orthogonal matrix A in which the determinant of A is 1 is of the form cos theta minus sin theta cos theta for some real number theta. This result we have assumed in the proof of above theorem. So I am proving it now. Suppose A is having entries A, B, C, D. Since A is an orthogonal matrix, A into A transpose is I. So you take up A and its transpose, that will become to I means 1 0 0 1. So if you multiply this, you get A square plus B square, AC plus BD, AC plus BD, C square plus D square is equal to C 1 0 0 1. Now equating on both sides, you get A square plus B square is equal to 1, C square plus D square is equal to 1 and AC plus BD is equal to 0. Now also determinant of A is what? AD minus, determinant of A is AD minus BC, that's equal to 1, or AD minus BC is equal to 1. You call this by number 4. Now you consider the case where A is equal to 0 and A is non-zero separately. Suppose A is 0. If A is 0, what will happen? Then by 1. If A is 0, then B square becomes, okay, B square becomes 1. B square becomes 1 means B is equal to plus or minus 1. If B is equal to plus or minus 1, then equation 4 gives, if B is equal to plus or minus 1, equation 4 gives C is equal to plus or minus 1. C is equal to plus or minus 1. And the equation 2 gives, 1 plus D square is equal to 1. C is equal to plus or minus 1, minus or plus 1 means equation 2 gives 1 plus D square is equal to 1 or D is equal to 0. Thus A becomes 0 1 minus 1 0 or 0 minus 1 1 0. Accordingly C is minus or plus 1. The first alternative, this alternative as a required form with theta is equal to pi by 2, because cos pi by 2 is 0, sin pi by 2 is 1, again minus sin pi by 2 is minus 1 and cos pi by 2 is 0. So with theta is equal to pi by 2, this is the required form. And the second alternative as the required form with theta is equal to minus pi by 2. Okay, answer now. So this is the required form with theta is equal to plus pi by 2 and theta is equal to minus pi by 2. Now consider the second case where A is, now we consider the second case where A is not equal to 0. If A is not 0, then the third equation gives C, the value of C to be minus B into D by A. Now substituting this value of this into the equation 2 gives as B square into D square by A square plus D square is equal to 1, or take LCM, B square D square plus A square D square is equal to 1, or B square plus A square into D square is equal to A square, or this gives A square is equal to D square, or A is equal to plus or minus D. Now if A is equal to minus D, then equation 3 gives minus D into C plus B into D is 0, or D times C minus B is 0, or C minus B is equal to 0. Okay, so this implies C is equal to B. And the fourth equation gives minus D square minus C square is equal to 1, or this implies D square plus C square is equal to minus 1, which is not possible because square of two positive terms cannot be equal to negative. Thus the possibility is A is equal to D only. A is equal to D. If A is equal to D, then the equation 3 gives, DC plus BD is 0, or D times C plus B is 0. This implies D cannot be 0, C plus B is 0. This implies B is equal to minus C. And so A is of the form A minus C, B is minus C, C and D is A. Now since A square plus C square is 1, since A square plus C square is 1, determinant is 1, there is a real number theta, such that A can be written as cos theta, B can be written as A can be written as cos theta, C can be written as sin theta, and A as a required form in this case also. Thus we have a required form. That means a very 2 cross 2 orthogonal matrix A with determinant of A is equal to 1 is of the form cos theta minus sin theta and cos theta. Okay, so these are the few results for this class, and I will continue the other things in the next class. Thank you for listening.